In this lesson, we are going to compare and interpret rates. A rate is a comparison of two amounts that are measured in different units. For example, keying 240 words per 8 minutes. That is an example of a rate. In this example, we have a 12-kilogram turkey that costs $42.89. We want to know what the cost is per kilogram. So when you're deciding on the rates, this is going to tell you which order you should look at reducing the ratio or dividing by, whichever way makes more sense to you. We want to end up with cost per kilogram. So that means we want to take the current cost of $42.89 over the current kilograms that we know, and we can set it up into a proportion. We are looking for the cost per 1 kilogram. Now, obviously, some of you won't need to use the proportion. Some of you will simply know you're going to divide $42.89 divided by 12. For those of you that struggle with this, proportions work for rates. So what we would do here is we would cross multiply, and then you can see we are going to divide by 12. So we have $42.89 divided by 12. We are dealing with money, so we need to round to 2 decimal places. So it's $3.57, and we put the dollars in, per kilogram. That is how we write our final answer. So do you have to go through all of that work? No. If you know you simply need to divide 42.89 by 12, you can do so. But if you struggle with this, set it up as a proportion, and then you can cross multiply and divide. Tom runs 400 meters in 1 minute 15 seconds. Joe runs 1 kilometer in 5 minutes 20 seconds. Determine the speed of each person in meters per second. So we want our final answer to be meters per second. So that means we are going to take the number of meters, we are going to divide by the number of seconds. That's ultimately what we are going to do. We can also do it through proportions. First, we will look at Tom. Tom's distance is given to us in meters, so that is good. But his time is given to us as 1 minute 15 seconds. So we first need to convert that to how many seconds there are. We know that there are 60 seconds in a minute, so we have 60 seconds plus 15. So he has been running for 75 seconds. So we want meters per second. 400 meters in 75 seconds. You could simply divide those at this point, but if you're still getting the understanding down, we set it up as a proportion. We now want to know how many meters he runs in 1 second. And we could therefore cross multiply and then divide by 75, which is ultimately what we had right here. But it just shows you why we are dividing 400 by 75. And he runs 5.33 meters per second. This goes back to how we wanted to write our final answer, meters per second. So now we want to look at Joe. We want to do the same idea, and we want to end up with meters per second. But Joe is not in meters. He is 1,000 kilometers, or 1 kilometer. What we need to know is that 1 kilometer is 1,000 meters. So he is running 1,000 meters. 5 minutes, 20 seconds. 60 seconds in a minute. So we have 300 seconds plus the 20. So he is running this in 320 seconds. So now we can do our meters divided by our seconds. And again, you could straight divide from here and you would end up with your answer. If you want to see why, we're looking for how many meters in 1 second. And when we cross multiply, we'll have 1,000 equals 320x, divide by 320, and we're back to the 1,000 divided by 320. But that is why it is a proportion, and we are trying to find the rate. 3.125, and we are doing meters per second. So we have determined the speed of each. And you could therefore look at who is faster. Tom runs further in 1 second. Tom also ran 400 meters versus Joe's 1 kilometer. When making decisions about buying a vehicle, fuel efficiency is often an important factor. The gas tank of Mario's new car has a capacity of 55 liters. The owner's manual claims that the fuel efficiency of Mario's car is 7.6 liters per 100 kilometers on the highway. Before Mario's first big highway trip, he set his trip meter to 0 kilometers so he could keep track of the total distance he drove. He started with the gas tank full. Each time he stopped to fill up the tank, he recorded the distance he had driven and the amount of gas he had purchased. On leg 1, he drove 645 kilometers and used 48 liters of gas. On leg 2, he drove 392 kilometers and used 32.1 liters. On which leg of Mario's trip was his fuel efficiency the best, and then draw a graph to compare each leg. So first of all, we want to compare his fuel efficiency, and the manual talks about it as liters per 100 kilometers. So that's what we should look at. We've got leg 1. Leg 1, he used 48 liters for 645 kilometers. We want to know how many liters he used per 100 kilometers that he drove, so that we can compare in per 100 kilometers. Because it wasn't per kilometer, it was per 100. So we can cross multiply. We'll get 4,800 equals 645x. Divide by 645. And we have 7.44 liters per kilometer, per 100 kilometers, because it was per 100, not just per kilometer. So 7.44 liters per 100 kilometers. Better fuel mileage than what the manual said. That's great. Leg 2. He used 32.1 liters for 392 kilometers. We want to find out how many liters that is per 100 kilometers. Cross multiply, we will get 3,210 equals 392x. Divide by 392, and you will get 8.19 liters per 100 kilometers. So a little bit worse fuel efficiency. Now, that strategy there takes you through using proportions. Some of you will be able to reason it out differently and you won't have to use proportions. That's okay. This is just how you get it. The other strategies are simply shortcuts because you have understood the process behind it. Now it also asks us to draw a graph to compare these. So we've got the distance and we've got the amount of gas that is being used. What we need to do is choose an appropriate scale. Now we are in the distances that we are going, the furthest he goes is 645 kilometers. So I could choose to use each scale as 50 kilometers. So here would be 100, 200, 300, 400, 500, 600, 700. The amount of liters, the most he has is 5. So I could choose to go up by 5. So this would be 10 liters, 20 liters, 30, 40, 50, and 60. So now, we start at 0 distance, and we haven't used any gas. So on the first leg of the trip, he goes 645 kilometers and uses 48 liters of gas. So we put a point right around here. And then we would join those points. So there was his first leg. Second leg of the trip, he starts again. Distance is 0, hasn't used any gas. We're going to compare. We go 392 kilometers, and we use 32.1 liters. Join those points, and we have drawn our graph. From our graph, you could see that the first leg of the trip, this was the first leg, this was the second leg. First leg of the trip had a less steep line, which means he used less gas for his distance, so he had the better fuel efficiency. And that was shown here mathematically. All right, in this example, we are given a graph that compares distance and time. It's showing how an all-terrain vehicle travels over time. Over which interval of time is the ATV traveling the slowest, and what is the speed? Well, if we look here, distance over time. So speed is distance divided by time. But if we have a look, if you ever have a flat spot, it means he's not going anywhere. He's sitting at the same spot. He's 30 meters from his start point, but yet the time is still going. So his speed here is 0 because he is stopped. So if we call this, let's label these. So from D to E, he is going the slowest, and it is a speed of 0. I guess this is in meters per second. He's not moving. Over which interval is he traveling the fastest? The fastest would be the most steep line. Now there are two fairly steep lines, and it might be difficult for you just to visualize to see which is the most steep. So maybe what we need to do is we need to find the rates of each. So let's find the rate for C to D. If we look here, his distance, he is going about 15 to 30 meters. So this is approximately a difference of 15 meters. Check our times on these. He is going about 16 minutes to 20 minutes, so about, or seconds, so in about a 4-second difference. So 15 divided by 4, he is going here about 3.75 meters per second. Let's check E to F. E to F is a distance of 0 to 30. So he's going 30 meters, and the time frame for this is in about 4 seconds. So from here, you should be able to see that he is going fastest from E to F, and it's about 7.5 seconds, meters per second. C. When does the ATV start to return to its starting position? So at A, it's where he started, then he travels, he stops for a while here from D to E, and then he returns to go home. So it's at point E, which is at approximately 28 seconds. When does it get there? It gets there at point F, which is about 32 seconds. And D, what does a zero slope mean in the context of this graph? So the zero slope is this part from D to E. What it means in the context of this question is that he is stopped. He is not moving, but time is still continuing. So his speed is 0 meters per second. So here are some key ideas. Rates can be represented in a variety of ways. The representation you choose should depend on your purpose. So you might show them by graphs, you might show them as meters per second. There's different ways you can show rates, maybe per 100 kilometers. The need to know, you can compare rates by writing them as rates with the same units, with second terms that are numerically the same. Or you can write them as unit rates, where the numerical values of the second term are equal to 1. So that would be like per kilogram. It's equal to 1. When comparing rates, it is helpful to round the values. This enables you to do mental math and express each rate as an approximate unit rate. In a graph that shows the relationship between two quantities, the slope of a line represents the average rate of change for these quantities. And the slope of a line segment that represents a rate of change is a unit rate.